So, you are interested in becoming a chemical engineer? This is the kind of stuff that you're going to have to do when you're at the desk. So, a company may come to you and say, hey, you need to come up with a process by which you can make a certain amount of product for us. Let's just simplify things and say that they're trying to make sodium chloride from two relatively cheap compounds such as hydrochloric acid and sodium bicarbonate. Okay? So they would ask you, okay, make for me this much. You're going to have to sit down and use the skills that you learn in first year chemistry in order to answer the very important question: how much reactants should I start with in order to make that much? Not more, not less, that much. Here we go. First thing we're going to have to do, of course, is come up with a balanced equation. That is the key to all of these things. So, bear with me. I'm having some technical issues. Sodium bicarbonate is NaHCO3. Don't confuse it with sodium carbonate, where we replace a hydrogen with a sodium. They're very similar and they act very, very similarly, but their formula masses are going to be very different. Plus, hydrochloric acid will form what? Well, this looks like it's a double replacement reaction. So the sodium goes with the chloride, and of course that is what we're expecting, but in an aqueous solution, which is what we're going to have. Sodium chloride, actually sodium bicarbonate is going to start out as a solid, and the hydrochloric acid is aqueous. And since sodium is an alkali, we know that it's going to result in an aqueous solution because all alkali metal ions are really swell. Assume their compounds are always soluble. Okay, so when there's a double replacement, it really results in just a bunch of sodium ions and chloride ions floating around. No big deal. When the hydrogen meets up with the HCO3, it forms something which is, of course, ringing all sorts of bells inside your mind, because carbonic acid is one of the two compounds that we know will further decompose into, in this case, water liquid and carbon dioxide gas. So this is a double replacement gas producing reaction. Double replacement gas producing reaction. So what do we know? We know that eventually we're going to need to make 1.00 grams of sodium chloride. The sheer power of stoichiometry is that if we know one thing for sure, in this case, that we need to produce 1.00 grams of NaCl, we can figure everything else out. So what we need to figure out right now is how much sodium bicarbonate or how much hydrochloric acid we need in order to produce for us 1.00 grams of sodium chloride. Okay, we're going to need to first of all decide who's going to be our limiting reactant, because once we know who our limiting reactant is, then we can just solve for this using stoichiometry. So should it be baking soda? Baking soda is a solid. It's relatively easy to measure. All we have to do is put it on an electronic balance or triple beam balance. Now the hydrochloric acid is not. Hydrochloric acid is a solution. most of that liquid is going to be water. There's going to be some hydrogen chloride dissolved in it. How much? Well, to tell you the truth, at this point, you really do not know how to deal with the stoichiometry, the numbers game around soluble materials such as acids. This is something that we will encounter later on when we talk about concentration, when we talk about molarity. So we really only have one choice here. We have sodium bicarbonate. That's going to be our limiting reactant. It's not going to matter how much hydrochloric acid we add. All that's going to matter is how much bicarbonate we add. So if we can, through stoichiometry, figure out exactly how much sodium bicarbonate we need, then we can add that to hydrochloric acid, and in theory it should produce for us 1.00 grams of sodium chloride. Okay, so is this equation balanced? Let's see. One sodium, one hydrogen, two hydrogens, one carbon, three oxygens, three, and one chlorine. Yeah, this is good. We got it. Everything's 1 to 1 to 1 to 1. All right, so let us begin. 1.00 grams of NaCl. Of course, step number 1 is to transfer all your grams of sodium chloride to the one unit that is in common with all chemicals, and that unit is the mole. So we're going to convert from grams to mole of sodium chloride, and hopefully by now you realize that for every 1 mole of sodium chloride you will have the formula mass of sodium chloride. All right, so now we're able to move from sodium chloride to what we need, which is sodium bicarbonate. Sodium bicarbonate. Where do we get these numbers? These numbers come from our balanced equation. That's an understood 1, and that is an understood 1. All right, so now we have eliminated grams of sodium chloride. We have eliminated moles of sodium chloride. Now we have moles of baking soda to deal with. And we're going to have to convert it to a unit that is actually measurable, because moles are not. We don't have any mole-o-meters. So, grams of sodium carbonate. And of course, just like over here, we know that for every 1 mole of sodium bicarbonate, we have the formula mass of sodium bicarbonate, which happens to be 84.0. So, take a moment, pause the video, and write this down, and then calculate. Go. Okay, so what did we get? We got 1.43 grams of sodium bicarbonate. So we're going to need to add 1.43 grams of sodium bicarbonate to however much hydrochloric acid will completely react with it. We should see some bubbles forming, because carbon dioxide is a gas, and eventually we should have a watery solution, water and ions. So we'll have a watery solution. So how in the world are we going to go from a watery solution of salt, sodium chloride, to solid sodium chloride? Do you know? Well, what if we heat it up and boil all the water away? The sodium ions and the chloride ions have nowhere to go. They can't leave with the water, so as the water leaves, it'll leave behind the sodium chloride solid. Okay, so what did I do? I got some sodium bicarbonate and I measured exactly 1.430 grams of this reactant. Then I took an empty test tube and measured its mass for reasons that you will understand. Notice there's a little bit of bicarbonate still sitting in that little pan. That's going to be important. Now I'm adding hydrochloric acid, and notice I just keep adding it. As I add it, then you see the gases. The gases coming out are carbon dioxide. That's just leaving. So that's mass that's going away. The water is still staying behind, joining, and so what you have there is a solution. It's mostly water, but there's going to be some sodium ions and some chloride ions. What happened to the carbonate ions? It's gone. It's gone. It's now part of water. It's partly water, and it's carbon dioxide. And every little bubble that you see go up to the top, that means that's more and more carbon dioxide leaves. So I did not start heating it until I noticed that all the carbon dioxide bubbles were gone. As I heat it, of course, the water boils away, leaving behind the salt. At this point, the salt is under so much concentration that it has actually affected the boiling point of water. Water is no longer boiling at 100 degrees. So as you can see, I have to hit it a little harder with the Bunsen burner, and I keep hitting it hard until there's no more noise of any water molecule that is still trying to get out. So what you see here is the mass of the salt and the test tube together. So what are the results of this experiment? Did we get our 1.00 grams? Well, it does not appear that we did. We did get quite a bit, and we can discuss the reasons why we did not get exactly 1.00 grams here in a second. First of all, how much did we get? Well, when you consider that the mass of the test tube was 17.0745, and then the mass of the test tube and the sodium chloride together is 18.0294, then if we subtract the two numbers, 0.9549 grams. That's not bad. That's pretty dang close. So, what does this mean? This means that we lost some sodium chloride, which you could not have seen because this does take some time. And I sped up the video. Is ever so often I would see a popper, a little popcorn. That's what I call some salt crystals that may have some water underneath it. And as soon as that water boils away, it kind of takes a little granule of salt with it. So I would see little salt crystals popping out of my test tube. Well, that means I lost some mass. So how much did I lose? It looks like I lost like 0.05, which isn't bad. Now remember, our theoretical yield is 1.00 grams. That was the goal. In theory, if I added 1.43 grams of baking soda to however much hydrochloric acid I needed in order to completely react it, which means the hydrochloric acid is in excess, then 1.00 grams is my, in theory, yield. Now, what is 0.9549? We call that our actual yield. That is what we actually got. So to find the percent yield, we take the actual yield and we divide it by the in theory yield, multiply by 100 to get 95.4. Let's 3 sig digs, 95.5%. So through this process, I was able to actually produce 95.5% of the product that I was ordered to provide. Obviously, the higher that percentage is, the more effective this process is. And as a chemical engineer, your job is going to be to find a process that gives you the greatest amount of percent yield. 95.5 is extraordinary. A lot of chemical engineers are going to be happy with percentages in the 60s or 70s. Sometimes they have to settle for 30s because this is the only way that you can produce this product, especially if the product is very, very expensive. 30% may be good enough.